Alright, in this video we're going to look at some of the formulas in physics for motion and unravel some of the mystery behind them. You see these formulas in both a calculus class and a physics class. So the first thing we're going to talk about is simple vertical motion. So if you have vertical motion, you throw something up and then it comes back down. And maybe you threw it from a distance of, let's say, S naught from the ground, and you threw it up with an initial velocity v naught. So gravity is acting on this object, and we'll call gravity negative g. That is the acceleration of the object, and it's constant. Now, if I integrate this gravity with respect to time, I get negative gt plus v naught, which is my initial velocity, plus a constant. So that constant is my initial velocity. This happens to be my velocity function, which sometimes in physics they put v sub y, meaning vertical velocity. In this case, because we're throwing it up and down and it's come back down, it's all vertical motion. If I integrate my velocity with respect to time, I get negative gt squared over 2 plus v naught t plus, let's say, another constant, we'll call it s naught. That's my initial height. So v naught is my initial velocity, so this is the initial velocity, and this s naught is initial height. And g is gravity. So it doesn't matter which planet you're on, these formulas work. Now there's one assumption we've made, that this is done in a vacuum. We haven't taken into consideration air resistance. But for our purposes, let's assume there's no air resistance. So this last formula is the distance function, sometimes called s of t or d of t, and again sometimes a y is used as a subscript because it's a vertical position or height. Now, what happens though if we throw something in a projectile motion and we're at a certain height here, a certain position, and we throw it up with a certain angle, let's call it phi? What happens? Well, let's think about this. So we throw it up like this and it lands back down here on the ground somewhere. So acceleration theoretically has two components, an x component and a y component. So if you want to be more correct than a previous problem, you can break down acceleration to two components. And the x component is going to be the actual magnitude of the acceleration times cosine, and I'm going to use a different angle, not phi but theta, because the acceleration may not be in the same trajectory as your velocity. And the acceleration, the y component, will be the magnitude of the acceleration times sine of theta. Now, if we're talking about gravity, gravity works up and down like this. And so in this case, theta would be a right angle. Just note that cosine of a right angle, 90 degrees, is 0. And sine of 90 degrees is 0. So if we're talking about gravity, the x component of acceleration goes away. And we only have a y component of acceleration, which is a sine of theta, but sine of 90, I made a mistake just now, sine of 90 is 1. So a sine of theta is just going to be a, and we'll call this a. If it's just gravity, we'll just call it negative g. Negative because it's pulling back down to Earth. So that's how we can break down these two components of acceleration to just gravity. Now what happens though when we get to velocity now? Because this velocity, let's assume this velocity, initial velocity, is in this direction now. So that's different. It's not working up and down like the initial velocity in our previous one here. What happens? How do we break down a velocity function? Well, let's see. Assuming the velocity is not perpendicular to the ground, we can break down our velocity function into two components. We could have an x component to the velocity and a y component. So the x component to the velocity is just my initial velocity times cosine of phi, because you want the horizontal component of this v naught. And that is the constant. If you integrate it, if you remember the acceleration in the x direction is actually 0, if you integrate that, you get a constant. Well, what is that constant? That is the velocity in the x direction, which is what we have here. And the velocity in the y component, well, let's integrate this formula here. Well, it'll be negative gt, which is this integration, plus a constant. What is that constant? Well, that is the initial velocity in the y direction, which is v naught sine of phi, that angle phi which you made with the horizontal. So that is the y component of your velocity. So these two functions are very important in projectile motion in physics. If you're thinking about throwing something that's not straight up and down, and the acceleration of gravity is negative g, these will give you the components of your velocity functions. Finally, let's say I want to know the distance. Well, x will give me the horizontal distance traveled, and y will give me the vertical distance traveled. So my horizontal distance, I integrate the top function, I get v naught cosine of that angle with the ground, phi, times t, plus whatever initial horizontal distance I may have been at. So let's say here's the origin right here, and I went across x naught. Well, that would be my initial horizontal position. And it could be 0. You could make the origin right where you throw from. And y now, my vertical distance, y, is going to be the integral of v sub y here, which would be negative gt squared over 2 plus v naught, the initial velocity, sine of phi, so that's the y component of my initial velocity, plus, if you threw it from a certain height above the ground, we'll call that y naught, the initial height. So x naught is the initial horizontal distance, and y naught is the initial vertical distance. Now, I want you to compare that to the equations we had with straight up and down, where we had s equals negative gt squared over 2 plus v naught, and I forgot here, there's a t, v naught t, there's a t next to this sine of phi, times a t. So v naught of t is the vertical plus s naught. This is straight up and down here, but when you're going at any angle, you tack in a sine of phi here against your velocity, and you have an x component with a cosine of phi against your velocity. So this is the breakdown of motion, and we can use this to solve many problems, as we'll see.